that has the effect of increasing the dispersal distance from the tree. And that's the name of the game, is spreading the seeds as far as possible. This project has been to add capability for winged flight to electronic circuit chips, with the idea that those capabilities would allow us to distribute highly functional but miniaturized electronic devices that could sense the environment for disease tracking, population surveillance, maybe monitoring of environmental contamination, and so on. So the objects that we've created consist of two parts. One is an electronic functional component that has an overall size scale in the range of 1 millimeter. So almost like a tiny grain of sand, but we've integrated with that electronic chip wing structures that form almost what looks like a helicopter. And so as these structures fall through the air, in interaction between the air and those wings cause a rotational motion that creates a very stable, slow falling velocity that allows these structures to interact for extended periods with ambient wind that really enhances the dispersal process, much like seeds do in the biological world. We think we've beaten biology in a sense.
Breathing on the fingertips because there's multiple actuators on the fingertip. Nice. Why don't you go ahead and try taking one of those blocks out? Is if you want to get rid of these little finger springs. An example of a more complicated interaction we could do with your hands. We can even shake hands. How often do you get to shake hands? You know, in COVID days, we were actually kind of missing that connection with people, right? Fist bump. You do fist bump.
Areas of life, bigger is better. But when it comes to microchips, smallness is boss. In May, a team of engineers at Columbia announced a new implantable medical microchip, so tiny it can be injected into a human body with a syringe. It's about the size of a single grain of salt. Chips like this one could eventually be used to monitor, diagnose, or treat medical problems. But there's a twist. The Columbia team's work also collided with the world of online conspiracy theories, much to their dismay. Before we tackle the misinfo, though, here's the real truth about injectable microchips.
Increasingly, there's growing interest in what can be done with actual implantable devices beyond what can be just done with drugs. So we're looking at implantables that we call chip-as-system devices. So these are devices in which the implantable is nothing but the chip. There's nothing else. This device is the smallest device that I'm aware of that allows bidirectional communication. Many equivalent ways you could calculate it.
Ken Shepard, a professor of electrical and biomedical engineering at Columbia, oversaw the team that developed the new chip. You've probably heard of surgically implantable medical devices, like pacemakers. The goal of projects like this microchip is to make medical devices that can be inserted and removed with less invasive measures. You can see the chip here being tested inside, yes, that's a raw chicken breast. So what exactly could an implantable device that minuscule actually do? The Columbia team hopes one day chips like these could detect the spread of cancers or monitor one tiny area of the body, measuring the presence of a particular enzyme or biomarker.
In this particular paper, we were just measuring temperature, which is a relatively easy thing to measure in a solid-state device. But you can imagine measuring all kinds of things. So, for example, we're working on measuring pH acidity or alkalinity of tissue, which is important in many functions. We're specifically looking at monitoring various biomarkers during wound healing to understand the wound healing process and perhaps even try to actuate in ways that would allow us to allow wounds to heal faster.
But getting here wasn't easy. Besides being extremely tiny, the engineers needed to power the chip wirelessly. It also needed to send and receive data.
One of the challenges with doing that is how you communicate with the device. So normally when we think of wireless interconnection, we think of using RF, right? That's the way our cell phone works. It's pervasive. Electromagnetics are pervasive in the way we interact wirelessly with devices today. The wavelengths typically for the kinds of frequencies that our cell phones use are on the order of centimeters in size. Devices we're trying to make are just fractions of a millimeter. 300 microns or about 0.3 of a millimeter. So it becomes impractical to communicate with them using electromagnetics.
The answer to the communication challenge turned out to be ultrasound. Yes, the same technology used to take candid shots of your future bundle of joy. Ultrasound's much shorter wavelengths made communication with a tiny device possible. Ultrasound is also how the chip is powered. An imager sends a request for information into the body. An element in the microchip essentially turns some of that ultrasound into energy, which powers the chip. That power allows the chip to act and send data back to the imager.
So as we know, ultrasound has been widely used